start with that. So how many folks in here are even familiar with machine learning beyond just a hurry? You're first. I should hope so. No, just kidding. But anyone else familiar with machine learning? Of what aspects?
Just building data queues and trying to build algorithms that pull data back out.
Okay.
Well, I've been doing it since undergrad.
Oh, perfect.
So all kinds of data image analysis, natural language processing.
Perfect. Well, as our sponsors mentioned, the very first part of doing all of this is preparing the data at all. So before you even think about preparing the data, I try to think about classifying it into two groups. This is very broad strokes, so this is an entry level, but I try to think of it in terms of you've got trained sets for data learning, and you've got untrained, where it's just loose and it's out there, and you just want to throw a bunch of information in the machine and see what comes out. So for trained data sets, which is pretty much what we're going to be talking about mostly tonight, I mean, we can touch on cluster analysis and whatnot later, but for trained data sets, it's really about getting the data down into a format that makes sense for the type of learning you want to do. So what do I mean by that? Start do we have markers?
Probably not. They probably got stolen.
No worries. But maybe we can just go ahead and fire this up here. So let's dig into one of these real quick. But for trained data sets, it's really about providing a whole set of information into the algorithm that you're going to use or algorithms that you're going to test. And I like to think of it as really just a big flat table, right, when you're first kind of wrapping your head around this. And if you can get the data into just what they call features and, figure out these are all the features of it. So for one of the examples that we'll go through tonight, it'll be a loan app risk rating app. And this is an actual app that we actually did put out there. But I'm trying to use a couple that are really simple because I want to get you guys thinking about what can I go into work tomorrow and actually go play with that by the end of the weekend. I can actually have some results that my boss might think is actually pretty interesting. So it's unbelievable how simple you can do some of this stuff even with just Excel. Now when you start dealing with really huge data sets, that's a whole other story. But I think there's quite a bit of value that you guys can get just with some of the out-of-the-box tools here. So when I very first started, it's all about what does the data look like. So for this particular one, let's go ahead and just take a look at it. And so here, this is actual data that we collected from a banking client. It's all been scrubbed, so you exactly understand. But we just kind of pared it down into these 8 columns. We figured we'll go ahead and start with that set. And these all came from loan applications. Like somebody came in and said, I want a loan for my house. Here's some information you gathered and collected. And the great thing about this set is we know whether or not the loan is defaulted. Because we're looking backwards a little bit. And so we can actually know, was the risk high? If the risk is high, that means that the loan defaulted. Or is the risk low? That means that, as far as we know, the loan went out to completion. Everyone was happy in the bank, had no issues with it. So for the purpose of this demo, this is the data that we had on hand. And so it was loan number, debt to income, loan to value, the credit score of the applicant, the employment code. So as far as the machine knows, it doesn't understand like if you're employed or unemployed, it's just a label in this case. So the feature here, we just use the EO for, owner of a company, H for homeowner, or housewife, I think is what we use that for, basically homemaker. And there were a few other codes in there. How many years they've been employed in their employment history, and their marital status. So, just from these 8 fairly straightforward things, we're trying to figure out, okay, if we threw this in a few different algorithms, would we be able to create a web service that now the loan officers, when they're sitting at their desk, it's a fairly small bank, they just want a rapid rating as to whether or not this is high or low to move forward. Can they just plug in this information and get a higher or lower score? And if it pops out low, maybe we go ahead and let it do it. If it pops out high, maybe we bump it up to the next level and run through our normal process. So this data was uploaded just using a CSV. So put the information into Excel. So as we're walking through the tool, I want you guys to kind of see the process that we go through, and we'll look at some of the more extravagant examples as we go. But the next thing that you want to do when you pop this open, so when you start a new experiment, you'll just have a blank canvas, right? So when you have a blank canvas, you'll grab your data set or your sample that you want to work on. In my case, it was the loan apps. And you just left click and drag it and drop it on the canvas, and that's kind of how you get it in here. And to add a data set, you just come here, say new data set, upload the file, pick your CSV that you want to upload, and it'll bring it in. So now that we've got the stuff that we want to take a look at, we need to go ahead and say, you know, which of these columns do we care about or do we want to feed into the machine learning algorithm? Now, logically, there's just going to be some information that you know is not going to have any predictive value, like the ID of the loan application, for example, or this one. So in that case, we just go ahead and, when this comes up, you can go ahead and pick some rules. And here I'm just saying, go ahead and begin with all the columns that are in the data set, but go ahead and exclude the loan number, right? Because really what's going to happen with this loan number is if it does happen to find a pattern or it's increasing, it's really just noise, right? So let's go ahead and not give the machine learning algorithm an opportunity to fix on something that we know is probably not interesting. So in the next one, so this next one I'm going to go ahead and take a look at and tell it, I want to go ahead and include risk. And so really what I'm doing here is I'm saying risk is what I'm going to go after and I'm going to try to learn. I want you to go ahead and include that, make sure that I understand it, and it's there, we've got it marked out. I'm going to tell it it's a string. I want to make it categorical, which now means it's kind of a label, like instead of just being a free-form string, it's one of a selection. And go ahead and label it. And label means this is what I'm going after. And you'll see in the next one, I'm going to call them features, and that's going to what the machine learning will go after if we're trying to predict values. So the next one is similar, except for this case. Obviously, I'm saying exclude risk, because I don't want to like label risk as one of my features that I want to have it used for the prediction. And I'm going to label all those fields as features. Now, this is where it gets fun. So, as we're doing this, we have to decide how much of this training data we're going to use to allow it to train the machine learning algorithm. How much of it are we going to kind of hold behind our back and say, okay, you've learned. Now, how well did you learn? And we're going to start feeding in stuff that we know the answers to so we can start scoring. And this will give us the ability to kind of compare different types of algorithms, see how accurate we think we are, see what the value of this is, or maybe we've got to tweak some of the different settings or parameters of the algorithms that we're going to be working with. But here we're just going to go ahead and say there. I'm not giving it a random seed just because in this case I want to make sure that I get the same result every time, just so it's consistent with that one. And then split stratify. I mean, you can read out that it's just how it's the settings. Now in this case, now add which algorithms do I want to work with. So now that we've kind of gone through the data sets, we've gone ahead and labeled it. As we mentioned earlier, there's a lot of work involved with manipulating it to the format you want. In general, I try to get it into the format that I like before I throw it into the tool. However, if you just want to plug in and there's just some simple transforms and filters that you need it for, there's quite a few built into this tool set. But you can kind of read through these, but a lot of them, depending on how complicated they become more and more important. Now there is one do want to call out when we get there. But so if you have a really big set, one very handy one here is the feature selection tool. So I'll show you another example where you kind of have a risk survey that's actually filled in for a company to go in and do an audit. And it literally was, are they an SEC company? Are they in the US? Are they FINRA regulated? And it would create a whole huge choose your numbers measure for answering this survey. The problem with that is it creates what's called a really large, sparsely populated data set. And all that really means is that in the world of answers for that survey, one survey may only have 20 features filled in, and the other 250 are just blank or not used. So when you've got that really sparse data set, it's next to impossible to eyeball and understand which ones may or may not have predictive value. So in the real world examples that you guys come up with, you run into that. One that's really handy that is going ahead and running it through a Pearson correlation filter. And I tell it, hey, let's just start with maybe 20 columns or find the 10 most important columns that you think may have predictive value. And go ahead and run your algorithm on that first. It'll scale it down, or it'll take the training size down, and it'll actually help out quite a bit. But this is one of those where you just kind of have to play around with it, but I wanted to point out because in the real world, people run into this problem a lot. Okay, so into the different types of machine learning. So in the really broad scheme of things that I've been talking about, like trained or untrained, they classify it in this tool further down to anomaly detection, classification, clustering, and progression. Now in my mind, I just generally say, okay, anomaly detection, I don't really know what's going to be coming in, but I want it to tell me when something's changed. So that kind of falls under the untrained learning set. So in that case, you're probably not feeding it stuff initially. You may, depending on the algorithm, but it's classically more of an untrained set. Clustering is another untrained model where it's just, hey, here's a whole bunch of data. Go tell me what's similar and put labels on it. And the computer's just going to put a label on it like 0, 1, 2, 3. You're not going to really know what the label is. It's going to be your job to make sure what the picture things are going. That's a bunch of people that tend to like to speed and crash. Okay, and we'll go ahead and label that high risk insurance. But I mean, you'll still have to go in and label it, and then after the fact, after you've labeled it, you can then use that label for a training set and start doing even more interesting things. But clustering can be super powerful, especially in real world problems where you're trying to find insights that you may not have thought of. Like how am I going to, perfect example is for an insurance company. They may have a whole bunch of policyholders out there. They've got a whole bunch of demographic data about their different constituents, as you would imagine, because they have to measure this. While they know a certain group of them are really high profitability policyholders, what would be really valuable as a marketing would be, let's run a cluster analysis to see if anyone else like that exists in my customer base. But I don't really know about that they fit this bill, because I'm not going to have a private client brokers call them up and start selling them services because they look a lot like the guys that bring them up on from the group. The other one that the clustering will also be good for is once you've labeled those groups, you can then turn around and go mine the social media of all of those customers' friends. And be like, yes, you look exactly like my demographic as well. The whole idea is just to get you guys that are dialing for dollars a heck of a lot more focused. You want to get their hit rates. I mean, they're lucky if they get 1 out of 100. If you can get their hit rates up to 5 out of 100, 1 out of 20, that's huge. And you can do that just by filtering that list out, or at least prioritizing the list of people that have to call. Makes sense? So before I start going too much further into this, what are some ideas that you're thinking about now in your business that you might be able to use some of these techniques for?
Throwing out, so I work for an HR and payroll company, so maybe employees that tend to get hired for
disgruntled employees can be really good. So, yeah.
I didn't see fire.
Yeah, I mean, actually on the HR side, one use that I found is very, very heavy is actually looking for employees that are about to quit. Because it's, I mean, like the disgruntled employees, the managers probably know who they are, but in that scenario, what can be really powerful is if you take your set of people that have left, right? You take their demographic information, their work history, you start thinking about what are the features like number of days of work missed in the last 30 days, amount of vacation time used in the last 90 days. Start thinking about what are the characteristics of somebody that left in those time frames and build up that data set. Go ahead and label it as employees that left, as you know, and you know when they left. Right? Now you can go train a model using this exact same technique, and once a week you can run the algorithm on your entire system and go, hey, these 4 people just went from probably happy to at risk of leaving. That's invaluable to a manager, especially if those are valued employees and just the cost of turnover of that particular job is out.
Doesn't that sort of skew the results though if it's like being observed? And granted it's all numbers and so forth, but like with this example there, if you're looking for a specific scenario where you're looking for people who get fired and you're looking for very specific numbers and then you train your computer to look for those numbers, wouldn't it possibly start skewing the numbers in the favor of everyone's going to get fired?
There is the possibility of doing what's called a pool check. So if you give it all examples of people that are going to quit, and then you run it through all the numbers, it's not going to know about people who are not. So one of the key things, and this goes back to data preparation and the art of it, is understanding what's the right ratio or the representative ratio of the population, so that when you train the model, it simulates reality as much as possible. So let's just use numbers that are easy. If there's 100 employees and your turnover is 10% a month, super high, your ratio should be somewhere around 90 employees that are happy and aren't going to quit, and you should have about 10 in there at all. And that's a pretty good ratio for a lot of these algorithms. Each of them have nuances to them, and as you do more and more interesting things, I always put up a graph on the level of effort and return on investment when I start talking about this with folks. But without even tweaking any of these levels to start tuning in, you can put in a very low level of effort and get a really high return on investment, and then you can triple that effort and only maybe improve the accuracy by 4 or 5%. Then you can quadruple that effort and maybe only get another 3 or 4%. So really, you have to understand the business problem and the return on investment for what you're trying to answer before you even begin. So all of these, if it's done in a shop that's fairly disciplined, always begin with what's the question the business wants answered. And so that's why I'm constantly throwing out there, how could you think about this in your business first, or what problem would you like to solve in your business that you haven't thought about before? I mean, there's always the determining the gambling or the spreads or who's going to win the game against.
Well, I was going to say, the other thing is you're not required to retrain your model. If you train it once, you can use that.
Yeah, and that's very true. I mean, unless the situations or if it's seasonal or if you've got something where just economics or demographics change, your models can be fairly static. And that's very true in stable industries, especially if the turnover hasn't changed. Absolutely. Yeah.
How can you tell, the pieces of data that are like labels, or that's the wrong term, versus you got I don't know, loan, or I can see debt, amount of debt, where it's the number actually means something. Does it automatically?
Yeah. So the computer has no idea what those mean. I mean, I could have had those columns be 0, 1, 2, 3, 4, 5, 6, and the feature names. It doesn't look at that in any way, shape, or form. I try to use meaningful ones that are fairly short, just so that in the tool, when I start looking at the results, I can understand what the ratios are, how consistent they are, what their statistical distribution is. I don't want to get too deep into the weeds So the next part here is like, so in this case, what we want to understand is this a high risk loan or is it a low risk loan? So out of the box with this tool, it gives you a whole bunch of classifications. And that's really what I'm talking about with classification, is just, you know, determine if it's high or low. Instead of saying, you know, is it 83% likely or predictive value, I'm saying, is it a 1 or a 0 or a -1 or a 2? Like, just give it a subset of labels just to tell me what I want to do with it. And so in this case, I picked a multi-class decision forest, and then here I'm making it off, and it's a 2-class decision jungle. Now, however, this can only go after one decision, so there's a little tool here that will allow you to take any of those from one multi. So basically, this will, instead of just looking at one feature, will let it happen against the rest of it. And then you literally just go through and say train it. So if I wanted to run it, I just go ahead and say select run. And now it'll go in and it'll load up the loan app data, it'll label it, it'll filter it. It'll just kind of start flipping through its problems here. And literally, I intentionally did not play with any of the default settings of those 2 different machine learning algorithms.
You explained two classes, and you know,
Sure. So those are classifiers. So under the covers, there's a mathematical algorithm that will execute. And it's a well-known technique called 2-class decision jungle. And I'll show you what the output of these are. But if you're uninitiated in the math, the idea is like it's been encapsulated in this one little tool or widget. And so as long as you know what to give it, and in this case, a labeled set of features, it will just, you know, execute it under the covers, save its trained model, and then allow you to use it in the future. Now, if you want to crack the code, if we have time, I'll show some of the more advanced models that were real life. I'll try to make sure that I rename things and protect the innocent. But in this case, it's really just without having to know the math. It's kind of trust that it works.
So without knowing how to run this and just trying to start playing with it, how did you know to pick those 2?
I didn't. You could literally, so, and I'll show you literally, like I picked a couple of them, and this particular experiment that you're looking at is in one of the samples, and it's just a way to bake off different algorithms and see how they compare to each other in terms of their results. Or you could have just built it by scratch, but usually it's easier just to start with this example and put your data sets in there. Yeah.
I haven't actually used this yet, but I saw somebody talk about it once before, and I think Microsoft has a flow chart to help you decide which algorithm.
They do. Yeah, it's a giant, goes on the wall, poster size, like a flow chart for, like, you know, machine learning, choose your algorithm 101. And as a matter of fact, it's a great tool that I used to use to train the guys that were uninitiated in the field for like what to give a shot. It's a great story. Thank you. That's a great point. But okay, so now we've got this guy up here. And so let's just go ahead and take a look at where they came from. So here, you can see I just grabbed the first one and the second one. Threw them out there and said, okay, how do they do? Now there's also a nice advantage of these in the fact that you can actually visualize how they make their decisions. So they're much better for demonstration purposes than say a state component vector machine or a neural net, which you can see how it makes its decision. So I just went ahead and dragged them and put them out here, ran them, everything worked the way it expected. So now I can go ahead and I can take a look at this trained model. So this is the algorithm. The algorithm connects to a trained model module. And the trained module, all it does is say, what's the data that I need to train it on? And what's the algorithm I'm going to use? So that's what these 2 connected points are. And once it's been run, you can visualize it. And now this particular model, being a decision forest, you can actually see what it did. And literally it just went through and created a whole bunch of choose your own adventure decision branches to determine whether or not this is a high or low risk project or loan application. So if I come in here and take a look at it, you can see in this, so this particular one, if you looked under the covers and the settings, it had a few. And one of them was, how many trees should I make to make my prediction? And the other one was, how deep am I allowed to make my nodes go? So these are just the default settings, so it creates 7 of them. And you can see, so for this very first branch, it decided that the first decision point for it is credit score. Now, if anyone in the banking industry would look at you and go, duh. So that's actually a good thing, because that means it's probably picking up things as they would expect. So what this says is if the credit score is less than 689, move left. If it's greater than 689, move right.
So left is false and right is true?
Cool. And you can see that here because now it's testing if it's less than or equal to 666. So rather evil decision branch tree here. So then we move on, it's like, yeah, if you're less than 666, you're high risk. We don't want you. If you're between those two values and you've been employed for less than 12 years, then it's got a whole bunch of things that it wants to think about. It wants to look at your debt to income. How many other outstanding loans do you have? If that's less than or equal to 42, you're out. If it's greater than 42, then it wants to look at your employment. Like, are you employed or not? Yes or no? So is your employment E? If the answer to that is no, you're high risk. If you're employed, we'll go ahead and give you a roll.
Are these all 100% here? There are cases where those would be less certain.
Yeah, so depending on the algorithm, it will come up with a value. In this case, at the bottom of the node, it's always saying 100%. And this is what this tree is going to contribute to this work. So this particular one, since it has 8, it will run your application through this tree. It will then run your application through this tree. And once it comes up, you'll see it better.
So is that like plot distribution there? The little graphs that are showing up behind
These little graphs over here.
No, not like periodically when your screen is refreshing, you'll see some different, it looks like graph lengths. Like credit score, it showed a blue line for a second and then went away. Is that just a refresh problem, or is that like actual data that it was trying to?
Honestly, I don't.
Right, help me.
My guess is a refresh, but
Oh, okay.
Is that 100% there actually the probability of zero?
well, it's what this particular tree will say in its contribution to the whole forest as to whether or not it's low. So some of the algorithms may have a different contribution level, and it depends on if you're using things that are non-reals. Like right now, almost all of mine are getting treated with labels. So like it'll have a different distribution, but at the end, like this particular branch, if it said, oh, it'll be 100% here. But my final score would be the sum average of all the trees. So if I had 7 trees that said it was low and 1 tree that said it was high, it would say that it's like 82.5% low in the final answer.
That's not probability, right? That's weighting for each of the trees.
Right. And so and you can say like, you know, how to weight the different trees. And, I mean, there's tons of levers under the covers that you can start playing with there, but I like to use this one for the first example because it helps you kind of visualize. We didn't come up with this decision tree. You know, we just threw the data at the computer and said, tell me what you think works. Right? And so then like taking a step out of this, now we also did it against this 2-class decision jungle, which is another type of algorithm. So now what we're going to be more interested in is how accurate, you know, was this one better or was this one better? So after the model's been trained and it's been scored, you can evaluate the model down here against up here. And so if I come down here and I right click and I say visualize, there you go. So what this little chart is showing you is on the left-hand side, it's our decision jungle, how well did it do, right? So when the actual score should have been high, the model said it was high 88% of the time. So without changing anything, we're 88% of the time we're right there. And a lot of times people call this a confusion matrix, like how how good did it do. This is just one way to visualize it. So 80% of the time it was good. And then when it was actually high, 12% of the time it said it was low. So you can see how in this case, since we only have two labels, high or low, those will sum up to be 1. And then on the flip side, when it was actually low, 22% of the time it said it was high, and 78% of the time-ish, it said it was low. And if you look at the algorithm on the right, the one we were comparing it against, it had a much better score on high and a similar score on low. So without even messing with any of them and the bake-off, I go, okay, well maybe this one's a little better suited. And I will take out my first one. And let's just go ahead. Let's do a normal one. And then the dead one, which is almost the right. And let's go ahead again. And now I just completely changed my mathematical algorithm I'm making it off against. I should see the same results on the right-hand side because I'm not changing my random seed. And on the left-hand side, I should see does it know that any better.
While that's running, what is your minimum N? What's the size of your sample that you can feel pretty confident about?
That is a great question. I don't like to approach this with anything less than about 500.
Okay.
But it really depends. 500 is really good to know. And it depends on how many features you have and how correlated the data is. So when you start going beyond something that's straightforward, like a loan application or a risk survey, or even a simple time series where you're just looking for anomalies and how it's flowing over time, you really have to understand what's the distribution of each of the features, which one could overwhelm the other features, so you may want to take it out. Which features are actually correlated, and that's actually what the Pearson correlation will help you understand. Because really what you don't want to have happen is have this beautiful, great set of, let's just say 5,000 entries, something small, right? And you've got 20 features that you think are fantastic, but in reality, 6 of those features are related mathematically, meaning that 5 of them are a function of one of them. Well, what's going to happen is the one that has 5 that are a function of it, it's actually going to overload and become the only value that's predicting the entire thing. Because all those other 5 are really just going to reinforce the one, and it's unduly going to weight that one. So you have to understand how correlated the different features are to each other as you start getting more complex. But the reason I brought up the Pearson correlation one is it does a really good job of trying to pick out the ones that are the most distributed from each other that aren't related.
Yeah, kind of related to that, is there any sort of way to evaluate how certain you are of your predictions in terms of modifying the data set? Like say, if I get twice as much data, can I predict how much better of a prediction I can make or anything like that?
Yeah, absolutely. There's a ton of techniques that you can go through to determine whether or not the change in your accuracy of prediction, the number of random permutations in your training set, all of those kind of start adding in, and then the level until you find the diminishing point of returns to say, okay, I added all this, but now it's just within statistical noise. I'm not really changing from one to the next.
Is there any way to make a prediction before you go bother to get that data that it probably will or probably won't help you, or how much it will help you? Or
generally, I like to start with all the data I can get hands on, and then prove that.
well, there's a lot of cost with the acquiring data. Right? As you increase it.
Yeah, you have to be realistic in terms of acquiring the data, but what's the cost of getting it?
Well, there's just development time to get more values into the system. Right?
Sure.
It's where the cost comes from. So just wondering if you had any ideas on how you would predict whether
Sort of going back
that's your
earlier.
effort would produce value.
Right.
You were saying how maybe you get up to 85% in a certain amount of data, and a whole bunch more coming each year, 5% of the way, right? That kind of thing.
And you can kind of chart it out. You don't necessarily know ahead of time, but in those cases when you're worried about what's it going to cost to get the data, I'd point you to our friends at Analytics and say, you know, they probably are really good at figuring out how to get it fairly inexpensively. Generally, I find that becoming less and less of the problem. Now, if you would ask me the same question 5 years ago, I'd be like, yeah, it'd be really expensive to use the data. Now, with the advent of cloud computing or commodity level computing, or, you know, large storage and scale, the extraction process is fairly expensive compared to the cost of the consultants or the data scientists that you have. You can just set your conditions, right? Just that cost ratio should be.
Excuse me. Is there such a thing as too large of a data set? I mean, is there a point where
yeah, there's diminishing returns, but really depending on the problem that you're
so you
trying
just
to
kind of
solve.
play with it and you do.
Yeah, so I'm sure.
So there is a point at which you can actually overtrain the model, overfit the model to specific data. So one of the goals of building machine learning models is one to be able to generalize it. You don't want it to predict 100% accuracy. You always have the data that you have, because you're going to get new data that you're going to want
Right.
to test. So there are techniques to assess how well you ever got something that you did with 100% accuracy.
And you know, some,
Well, I mean, that's not uncommon. There are some situations where you can build a model that fits the kind of data that you have. Okay.
but
But you lose predictive validity. When you have something that always gets it right out of your training data, you have no idea whether or not you're going to get a difference in some new data that your model hasn't seen before. So typically with the training models, you're looking for something that's highly accurate but not perfect accuracy. And there are additional techniques which I don't know if there's anything in this suite that can help you do those kind of analyses. So that's a whole class and multiple classes. Advanced mathematics.
Right, yeah, so all these statistical functions are exactly to help with that type of thing. So there's a lot built in, but we would definitely have to start diving into some math that even I probably not want to have. So I'll try to stay out of those areas. But so we went ahead and we trained up our neural network against it. Let's go see how it did. And pretty miserable. You know, didn't do much better. Neural net, at least with its default settings, did not do any better than the forms. Now, you know, start reading more about neural networks, start looking at the number of features you have, start thinking about how many layers, connected nodes you need, and that can dramatically change. Start doing interesting things like having neural nets create a feature that then feeds the next neural net. That starts getting into a whole other area of science in terms of how to stack these models on top of themselves. But as you can see here in this case, if I'm just going out of the box and trying something, I'm going to stick with, you know, player number 2. And you can just start going through here out of the box, just to get yourself familiar, executing each of these different algorithms against each other and seeing how they play out. And I'd also recommend taking a look at what they show you when you actually run. So this means a lot of really good stuff to someone that's studying neurons. But it's really okay, and it's something that you guys are going to want to be aware of if you're using this for business purposes, especially if you're using it for a loan app or insurance or anything where you're offering a service to the public. A lot of these techniques can't even legally be used to make a business decision. So let me give you an example of why. One day when I was at an insurance company in Chicago, and it was good things, they actually, we're experimenting, as you can imagine, in the actuarial tables. This is a big field in that area. But I learned a really interesting thing. We can't use anything that's unpaid. Because when you run the data set through the user base, it's going to group and cluster rate things socioeconomically, by race, and by gender. And the computer knows nothing about race, gender, and socioeconomics, but because you can't show how it made the decision, you can't prove that it wasn't biased. So you can't use the results of the algorithm.
So we should just exclude those fields?
It's not that you would, even if you exclude those fields, that's the amazing thing. So like, let's say that you want income, debt to income, loan to value, number of accidents in the last so many days. You just start thinking about all the things that you would think of would have nothing to do with that. It will still group them in those categories.
So just for the details, we'll look at the breakdown into categories, and categories are broken down by race. They don't care, put it out all about people in one category, what's the second category. It doesn't matter if you think we're legal or weird, it doesn't happen.
Well, because it happened, and you can't say why it happened. At least with the decision forest, you can go up to a regulatory board, and you can go, we went from here to 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 here, and you can see every step of the way had nothing to do with us being biased, and we apply this universally to everyone. You're good. Crack open a neural net. Okay, so why did I make that decision? I don't know. There is no mathematician that can tell you why. Like, it's just so intertwined in how it like learned its coefficients for doing its calculation and how it's reinforcing its network. You can't make heads or tails of it anymore than we make heads or tails of the data sets just looking at it. So because we can't defend it, the regulation and laws of math products might have changed this a few years ago in the previous slide, but at least last time I checked. So that's something to be aware of if you guys start using this in your day-to-day life. If it's anything like the impact of your regulated along those lines, just kind of keep that in mind before you go into detail. So any questions on this? Or how to, because really what I'm hoping that you guys will get out of this is if you leave here tonight, you go sign up for a free account, load up some data that you think is interesting, start dragging around the boxes and hit play. So, I mean, do you guys have any questions on how to set something like this up from scratch?
I just go back to the analogy. Is the neural network the only one that isn't transparent in how it has results?
No, sticking component vectors are not transparent. And then, like, so some of the other fun ones that we're not using here because we're trying to label, high or low. But like the regression system, so like let's say that you're trying to figure out a point system for one. That's a common, entry data machine learning algorithm class, right? Trying to figure out what the point system of the line is based on what the weather was, what the land is like, how memory actually grown, its geographic region, how many cold days there were, et cetera, et cetera. If you want to come up with like a point number or some range calculation, those will be in the regression section. And again, that Microsoft, poster is a great starting point.
So a question, so let's say that I want to we're kind of use this play around with it, but I don't really have like a good data set ready to go. An idea of trying to find some sample data set and come with just something that, practice.
All of these on their own. So if you guys suddenly want to come up with your own, just go nuts. What I really recommend is there's a library out there. There's like a store of different machine learning techniques. One of the ones that I love the most is kind of predictive failure for jet engines. You can literally just go to the store, look at all the samples, say, put that sample in my notebook. It'll fire up. It'll put all the blocks together. It'll put all the training data sets in there. And then you can literally walk through it. It's got a nice tutorial on like why they chose this, how the settings worked. So like if you really want to start digging in. I mean, like one of the most fun ones that we had done just not too long ago in the recent past was, if you guys ever gone to Home Depot or Lowe's and got paint, the number one profitable thing in that store is paint. If those paint mixers go down, that store is freaking out. A lot of times they will actually have a spare paint mixer in the back because their margins on paint are so high. And if you walk in and you need eggshell white and their paint mixer's down and it's the weekend and you got to go to work on Monday, you're going to walk right out of their store, right across the street to Lowe's, and you're going to buy the paint you need to finish your job. So they want those paint machines up and running at all times at all costs, to the point where they'll have extra machines sitting there. But there's a funny failure that happens when you have a paint machine sitting there and you're not using it. When you go to use it, it fails. It's not been cleaned, it's not been maintained, it's sitting in the back where it's dusty. Okay, so great, we'll put 2 paint machines there. Well, you want to know what happens there? Sally likes this one. John likes this one because it's easier to get to. One of them gets underutilized, the other one gets overutilized, and now you've got a maintenance and a cost problem. But that's actually better than having to run on those pumps. So one of the things that we did is it actually turns out each paint color, the effluent, so like the paint mixers have 16 nozzle heads. Each nozzle head has a different type of fluid in it, and each fluid has a different failure ratio than the pump heads and duty cycle. And so good luck figuring out when you need to go maintain that machine if you're trying to do it on the back of the house. So what we did is we went through and we took all their data, all the stuff they had on failures, all the different fluid stuff that came out of the labs, and said, okay, every time you trigger, tell us the number of turns on the pump, what was in the pump, what time it was, because even the time, so like they had problems where one color in the lab they couldn't get to fail the pump, but in the field it would fail the pump all the time. And it actually turned out when we were looking at data that if that pump had like I think it was like a 16-hour window to dry and then it was used again, it would start building up. But if it wasn't used long enough, it would evaporate and clear itself. And if it was used continuously, it would build up. So I mean, the weird things that they could duplicate the lab. So we came up with a little system that had, here's a map. Here's where every one of our paint mixers are. Here's the store it's in. Here's where it's located on the floor plan. Here's the color indicator on every one of the nozzle heads. Here's the expected remaining useful lifetime based on its usage. And now when the guy goes in to do the regular maintenance, instead of going on a 3-month schedule regularly, some stores they can show up 2 months every 6 months. Some stores all of a sudden he just went to because he knew one of the paint heads was going to change. And then his little app also told me the one next to it's about me. So since I'm here, I'll go ahead and do it. And it drastically reduced their cost to maintain these and gave the perception of 100% uptime for their clients. Hugely up. That whole process took about 4 weeks from start to finish.
So how about things that you can't necessarily quantify or observe other than from like third-party perspective? The idea that comes to mind is, say, you're wanting to build a thermally efficient custom PC, but you know you have a case in mind, you have coolers in mind, but you don't necessarily know which ones go together. You know, like maybe the heat feeds are like this, but they need to be going like this. You know, just various different reasons that might either hinder or help the situation at hand. So how can you build a model based off of essentially unknowns? Is it
Great question. I would have to do a lot of time to approach that. I mean, you could do some kind of regression model if you knew the thermal characteristics of the fan being this way versus this way, the conductivity of a certain. I mean, you could almost just regress through, but that's more of a brute force. But regression fits in fairly brute force to begin with. But I'm not sure if that one would work well for these techniques.
You might, if you actually built every possible combination. No, if you built a bunch of combinations and then trained a model on that, you could then say, given this GPU, what are likely my best, get literally like down to like, Asus's Strix or whatever, such and such, GPU, what's the best case that you can use for
Yeah,
this?
so like if you start thinking about it in terms of a table, right? And you label it successful, or maybe you want to determine the temperature of the internal case as well, right? That could be what you're trying to predict. And then you have things like GPU, metal of heat sink, metal of case, spacing case, fan RPM. You just start thinking of all those types of features, and you've got enough examples that you can feed it. When you set it a new configuration, it'll come up with a rating for how hot you think it is. It's not needed based on those different decision trees that it comes up with. Because again, that's really no different than the example we're looking at here in that case, because it's low versus low higher. It's a regression model. So like if you can use it for decision forest to come up with a regression number, right? It'll set out like whatever that range is. That's one way you can do it. you're training and not something. Okay, so now that we've gotten here, and let's just say that we really like our friend over here that's trained. We can go ahead and take a look at it or whatnot. But where it gets really fun is you go ahead and publish this. So we've done all this work. We've got a model of work. We feed it these 8 features. It'll tell me if it's high or low. Well, I want to use it. Let's use it real time. All you have to do in this tool is go down here and hit publish. It'll set up a web service. It'll let you do real time and batch. And it'll spit out the answer. It'll give you the REST endpoint API. It'll give you the C# sample code. It'll give you the, there's like 5 other languages in there. You use JavaScript and use the sample code for it. And go plug it into your app. Or in this case, we just use the out-of-the-box Excel spreadsheet. You can literally just say, go download the Excel file that hooks up to this through the web. Fill in all the fields that you want, hit fill rating, and literally all of a sudden in Excel it will populate with the rating of the new features on the left-hand side. You're done. It's literally that simple. Using that method, it'll create a web service over here.